Well, good morning, dear. Welcome back. This is lecture number 5. In the earlier lecture, we discussed about modeling technique of robots, and in a very generalized way, we discussed the basic concepts of forward kinematics, inverse kinematics, forward dynamics, inverse dynamics. These are essentially the concepts which are applicable to all robots, and they are really will be the main focus of this course. Today we are continuing our discussion regarding robot modeling. Here I am trying to give you a clear picture how a robot as a mechanical structure can follow the commands of ours and it can work. So morphologically it is designed keeping an eye to the intelligent creature, the greatest intelligent creature, human. That's what we claim. So morphologically they are similar. So robot has following components. Number one, links. Okay, this is a mechanical structure. Just like we have limb, okay, various limbs are there. So robot has links, okay. And our limbs are actually moved by actuators. We call them, technical term is actuators. For us, the actuator is muscle, okay. So muscle is actually making movement in our limbs. For robot, it is called actuators, and there are different types of actuators. Say electrical motor type, and both DC servo and AC servo motor are used. DC servo nowadays, AC servo motors are also used. Okay, so we will discuss detail when we will come across about in our actuators. And for heavy duty robots, for example, robot deployed in construction robot, okay, the actuators could be hydraulic in nature, okay, they can carry a heavy load, okay, so this is, and there are other types of actuators is pneumatic actuators. They are operated by air, okay, and sometimes hybrid actuators, that is electro-pneumatic, electro-hydraulic type of actuators are used. Okay. Another major component of robot is sensor. Okay. Sensor enables robot to actually interact both internally and externally with internally with the commands and externally with the environment. Okay. There are various types of sensors. Say for example, tactile sensors. Tactile sensors are those sensors which are activated by actual touch. Okay, activated by touch. Okay, say for example this potentiometer type sensor, piezoelectric sensor. Okay, once you touch they issue signal, and once you calibrate they can act as a sensor. Another type of sensors are non-tactile type of sensors. They are quite large in variation. Here the signals are issued without physical touch. Okay. Two broad categories are actually non-tactile sensors: proximity sensor and this is the vision sensor. Okay, one is proximity sensor. That is, proximity sensors are those sensors which if you come closer to the proximity to the transducer, it will issue signals. Okay, piezoresistive sensor, piezoelectric sensor, all kind of sensors are non-tactile proximity type of sensors. Okay, and the most important and the widely used sensor which is making robot really smart is called vision sensor. This is just like our eye, trying to imitate our eye, of course, in a very small way. But this is the most important sensor which enables robot to see the world and act as per the command after visualizing its environment. Okay, and these sensors we will discuss in detail in the class. Okay, and then the another most important. So you have links, physical structure. You have actuators which causes movement to the links. You have sensors, but will robot work? No, because you need control. Just like human having all sensors, limbs, actuators, the control system which is brain and spinal cord in case of human, if those controllers are not there, then the human structure cannot move logically, right? Similarly, for robot we have control and trying to imitate human. In robot also we try to divide the control into two separate parts. One is called planar level control, which is trying to imitate our central nervous system or brain. Another is execution level control, which is trying to imitate our spinal cord. Okay, so planar level controller, which is a computer essentially, is trying to solve all high level planning level tasks. Say specifically in robot, they are actually solving forward kinematics, then inverse kinematics, trajectory. They are planning trajectory. They are also solving forward and inverse dynamics. So all kind of, they are also calculating Jacobian. So all these high level computation and planning will be done in the computer. Okay. Say okay. So this is our planner, okay, which is essentially a computer. Then we have so this is computer or planner, which plans. Now planner actually is connected through interface to this is interface. Planner is through interface, it is connected or giving command to execution level controller, which are actually processor, microprocessor, which are mounted at every joint. Okay, say joint 1, then you have microprocessor which is controlling joint 2. So if you have n number of joints, essentially you need to have n number of processor. Okay, so they are actually responsible for moving the joints. Okay, and of course they are getting command from the boss, that is the planner. Okay, so this is two-way communication. That's why I am giving them, writing them with the arrow. Okay, two directional arrow, bidirectional arrow. So this is basically the morphological structure of a controller. Planner does all kind of planning level activities. Then the result will be some output. Okay, say we are trying to move a robot. Okay, so it has an actuator here situated on here, motor. Okay, here another motor. So these motors are actually getting direction that how much to rotate so that it will come to theta 1 degree, it will come to theta 2 degree. So how much to rotate theta 1, theta 2, these computer will tell that. Okay, this is a very simplistic view I am trying to give you at the first time. And then once it is given, it will go to the microprocessor, right? And then what microprocessor will do, processor means it has, lots of memories. Okay, lots of memories are there. Say this is 4-bit memories. Okay, lots of memories. So let me first draw on the block diagram, which will illustrate what it is doing. Okay, then you may need some amplification of the current, so we are keeping a block for that, and then you are feeding it to the motor, suppose motor number 1. Okay, this is a typical example I am giving for a armature current control. Say this is what you are getting from the boss. Okay, that is the planner. Okay, and then you have a sensor here. Without sensor, control will be useless, only bang type of control. Okay, so normally robot will have sensors. Okay, so how this is the joint level. Say I am actually drawing. Very simple, just you listen and then you will be able to know. So this I am drawing in a elaborate way. Okay, so theta actual, and these are actually, please remember, these are all function of time. Okay, now let us see. The planner has issued some command, okay, that is set value theta d, okay, for every joint, and then those values are going to the microprocessor. Microprocessor is getting that value, and then it is sorry. Let me correct it. So and then microprocessor is keeping it in its register. It has lot of register or memory. Okay, and then it is checking the motor's position. Okay, normally we have encoders. Okay, as a position sensor. Okay, this is called encoders, and these are essentially the internal sensor of a robot. They are mounted on motor shaft. Okay, so motor shaft through this sensor will tell microprocessor that what is the current angle which the particular joint has joint is in position, right? And it has a command. So this is desired value, this is actual value. So this is kept in one register, this is kept in another register. Then you can compare, microprocessor will compare the content of the two registers, and if there is any error, positive or negative, of course it will have to act. The error should be, so far everything is digital, and that cannot move a mechanical structure, right, physical structure. So there is a block which will convert that digital signal to analog signal, and obviously this is not a power electronics, so this signal will be very weak. So that's why normally we need to amplify that signal, so it will go to the amplification box like this. Okay, and then amplified signal, suppose we are talking here about armature current control. Okay, so there are so many controllability issues here. The simplest one in case of motor, I am giving you an example that we are proposing to make armature current control. So that amplified current will go to the motor and it will rotate the motor. Okay, again its sensor will sense, and this thing will continue till theta d and theta actual is near about 0. Okay, so every joint is undergoing this thing. if you have several joints, there will be several such activities going on. Okay, and that is an interface. A very vital role it plays. You see, the planner is only planning. Okay, say normally in case of Puma robot, which we will discuss, it issues signal in the interval of 28 millisecond. Okay, so after solving inverse kinematics, trajectory planning, it is issuing some values. Okay, and those values are going to all the joint. Okay, now suppose this joint is actually at the end joint, right, and which requires very small movement, only one link movement. Okay, but you see, if you have the robot is a serial link, right? So suppose these, and you have so this joint, and this is say theta 1, theta 2, theta 3, theta 4. Okay, so theta 1, theta 2, theta 3, theta 4. We have 4 joints, right? So planner has sent a set of 4 values. Okay, so and they have gone to this respective microprocessor, which are situated here together with the actuator. Okay, and this motor only need to rotate this link. This motor need to rotate this and this link. This motor need to rotate this and this link, and this motor, of course, okay, need to rotate this. That means need to carry the load of this link, this. So the work done for this motor will be much more than this and then this and then this. Is it clear? So suppose at a time all of the joints have received the command, but this will finish its job earlier. So interface, keep an eye to this actually. Okay, so every joint has an address. Okay, so it is monitoring which joint has already completed the task and which has not yet completed. So because unless all the command in totality is executed here, then there is no point of giving another set of command, right? So interface, like an orchestra controller, it is actually doing this control job. Okay, it gets all the information, okay, from all the joints. The moment it is done, it will issue a signal that I am done. I am done. This joint I am done. So interface will see that all the joints have really executed the task given to them before issuing a fresh signal. That's why 28 millisecond interval for Puma robot, okay, it takes 28 millisecond, whereas this loop actually works at a rate of 0.87 millisecond. Okay, so this is very fast because in one go you will not be able to move the link to the desired value. So many iterations will be required. So that's why this has to work very fast. Okay, and once this is becoming the error is becoming this error-driven system, feedback control system, error is becoming 0 to a 0, then it is done and it will send a signal that I am done here. Similarly, all the joints will do that. So in this coordinated fashion, this is called master-slave architecture. Of course, nowadays this terminology are not very good, so let us not call anybody master or slave. Actually, there is another nomenclature. This is planner level, this is execution level control. This is planner level control, just like our brain, execution level control, just like our spinal cord. There are another names also. This is planner, executor, high level control, low level control. Low level means they are not doing any low level job. Please remember, low level here means that they are actually doing the job. This high level controller can only pass order, okay, in the form of digit. which is useless in rotating a joint. It requires an executor. So without low level control, high level controller is incomplete. So this architecture is very, very important, and we'll definitely discuss more on this issue. Okay. The microprocessor, on the other hand, is computing, as you know, several controls law which we'll discuss, PID, PD, as the case may be, and then executing the task as proposed by the planner. Okay. So in short, this is the way the robot actually works. Okay. So it has mechanical structure, it has mover which is moving, what's called actuator, it has sensors which actually it is seeing the environment and interacting with the environment. Also internally it is keeping a balance between commanded signal and internally generated signal through internal sensors like encoders. Okay, so with the help of different kinds of sensors, with the help of proper control, a robot will follow the robot will follow the order of order of ours through programming which we are doing in this computer. Okay. So this is the story I wanted to tell you in these 5 lectures. Now we need to actually see how can we do this job step by step. How can I represent a structure in the form of a matrix? Okay, because matrix is very easy to program. Okay, this essentially we are talking about spatial transformation, how transformation can be done, because what I have shown you here so far, they are actually very simple schematic manipulator. They are not robot. Actually, in case of actual robot, how it is done in the subsequent classes, we will discuss one by one. And now we are in a position to talk about how to represent links. Okay, so we'll in the next class we'll talk about spatial transformation. Till then, stay safe and goodbye.